Today, we are undertaking a truly fascinating mission. We're diving into the life and work of Johannes Kepler. And this is a figure who stands, just squarely at the fault line between medieval world and the modern one.
Right. It's a time that's just defined by religious zealotry, intense political turmoil, and at the same time, this radical intellectual progress.
And Kepler is right in the middle of all of it.
His name is, synonymous with celestial mechanics, but the man himself is just this enduring paradox. Our source material paints a portrait of a profound, almost mystical religious thinker. He fundamentally believed in a divine geometric perfection.
And yet he's the person who laid the rigorous mathematical foundation for modern physics. He directly paved the way for Isaac Newton.
So our mission, really, is to understand that contradiction. How did Kepler manage to bridge that seemingly unbridgeable gap between these, spiritual, philosophical systems and what we would call cold, objective, physical science?
Well, his published works are astonishing in that way. They're not dry scientific papers. You can open any page, and you might find these intense personal notes, detailed religious reflections, these bursts of mystical enthusiasm.
And right alongside them,
Meticulously composed tables and undeniable mathematical proofs.
it's not just a fusion, is it? It's a deliberate mixing of elements that, in his mind, were absolutely connected. They were necessary for understanding the cosmos.
I think the sources argue this really compellingly. They say that while others might have eventually, stumbled upon the discoveries of Copernicus or Galileo, no one else
could have done what Kepler did.
Exactly. Not with the tools, the data, and the prevailing philosophy of the early 17th century. It required his unique, paradoxical genius.
And his legacy is just titanic. We primarily remember him for the 3 laws of planetary motion, which, finally provided that elegant mathematical framework for all of Tycho Brahe's lifelong observational data.
And it confirmed the Copernican system not through philosophy, which was the old way, but through computation, through hard numbers.
But it goes beyond just astronomy. He pioneered the field of modern optics, he formulated the true theory of human vision, and perhaps most importantly, he took these critical first steps toward developing a theory of universal gravitation.
Almost 70 years before Newton published his Principia. It's incredible.
It's a huge amount of material, but I think before we can even analyze those cosmic rules, we have to unpack the sheer chaos of his existence. To understand the precision of the laws, you need to understand the difficulty of the life that produced them.
I think that's absolutely right.
So Kepler was born in 1571, and as you mentioned, his early life was characterized by a level of instability that makes his eventual concentration on minute astronomical detail seem, miraculous.
Miraculous is exactly the right word. He chronicled his own difficult beginnings. He noted that his father, Heinrich, was a soldier, corrupted, crude, and quarrelsome.
Not exactly a glowing review.
Not at all. His father frequently disappeared, joining mercenary forces like the army of the Catholic Duke of Alba, and then he eventually just vanished entirely, leaving the family in constant poverty.
And his mother, Katharina, he described with equal frankness. He called her small, dirty, talkative, and quarrelsome.
This was just not a stable, nurturing environment. They came from a once noble family that had fallen into deep poverty. They were frequently living in these cramped, substandard conditions, like a house built above an animal shed.
And on top of that instability, you have his persistent ill health.
Yeah, as a child, he contracted smallpox. And while he survived, it left him with these lasting visual defects. Crucially, he suffered from severe myopia, so nearsightedness, and also polyopia.
Polyopia. That's double or multiple vision, right?
Exactly. So just think about that for a moment. This is the man who would demand observational accuracy down to a handful of minutes of arc. Yet he was severely visually impaired.
So how did he deal with that? It's a fundamental handicap for an astronomer.
It was a monumental struggle. And it's one of the reasons why he relied so heavily on Tycho Brahe's data later on, rather than his own observations. He personally noted the impact. He recalled that when he looked at Sirius and the full moon, they appeared to him to be the same angular size.
Which is physically impossible.
Completely impossible. It meant he couldn't perform the precise sighting necessary for high-accuracy astronomy. So it forced him to focus on the mathematical and theoretical models, elevating the importance of geometry and analysis over pure observation.
And beyond his family troubles, the background hum of 16th century Europe was just this constant religious strife. Kepler, a devout Lutheran, found himself caught right in the middle of it all.
This is a crucial point. He was constantly moving. He was exiled from Graz, Prague, and Linz. And it wasn't just because he was a Lutheran. It was because he held these sophisticated, nuanced religious views that were acceptable to none of the prevailing sects.
He didn't fit in anywhere.
Nowhere. He sought this theological unity among all Christians, but he was rejected by the conservative Lutherans, the Calvinists, and the staunch Catholics alike. It just left him politically exposed and without refuge.
And this persecution became deeply, tragically personal. His aunt was declared a witch and burned alive.
And then in 1615, the accusations turned toward his own mother, Katharina.
This is, for me, the most astonishing part of his life. The sheer coexistence of chaos and genius. The case against his mother dragged on for 6 agonizing years.
It started with minor quarrels with neighbors, but it just snowballed into charges of poisoning, witchcraft, summoning the devil, the usual stuff.
And during this entire period, Kepler, the imperial mathematician, is serving as her primary defense lawyer.
And not just in name. I mean, he was deeply involved in the legal strategy. He was writing these lengthy, complex defense memoranda, arguing against the use of torture, and leveraging his reputation to negotiate with the authorities.
The intellectual strain must have been unimaginable.
I mean, think about it. One day he's refining the orbit of Mars, attempting to find the perfect harmony of the spheres, and the next day he is fighting to save his mother from being interrogated on the rack.
He was even at one point physically trapped in Linz because of a siege during the 30 Years' War, so he couldn't even personally defend her.
Yet he kept working. He kept writing and he kept directing her defense from a distance. And his dedication paid off. He eventually secured her release in 1621.
Though she died just a few months later.
Yeah, the ordeal took its toll. But this resilience just demonstrates an immense capacity for concentration. He literally solved the mysteries of the heavens while the world around him was collapsing into war and superstition. It shows us that his intellectual life wasn't a luxury for him, it was a sanctuary.
So, despite all this turmoil, his education offered some crucial anchors. He gained a foundational knowledge of Latin, which was, the key to the intellectual world back then.
And crucially, he was mentored at the University of Tübingen by Michael Meslin, his astronomy professor. Now, Meslin was deeply aware of Copernicus's heliocentric model, but because it was considered heretical, he taught it secretly.
Only to his most promising students.
Exactly. And Kepler immediately recognized the elegance and the rationality of the sun-centered system. He became a lifelong, staunch advocate for Copernicus.
He seemed primed for it from what the sources say about his youth.
Oh, absolutely. He recalled his mother taking him up a hill to view the Great Comet of 1577. Celestial events held this deep significance for him. He also vividly remembered his father showing him a total lunar eclipse in 1580, where the moon appeared a striking bright reddish color.
A phenomenon he would later explain through his work on optics. The cosmos was calling to him from a very young age.
It really was.
Now, let's confront the elephant in the room for any early modern scientist: astrology. He called it the stupid daughter of astronomy. Was this a necessary evil for him, or did he genuinely believe in some form of cosmic influence?
It was both. I mean, as imperial mathematician, he was contractually obligated to produce calendars, annual predictions, and natal charts for his patrons, princes, emperors, kings. It was his income stream.
And he was actually pretty famous for it, right? He made some successful predictions early on.
He did. He achieved significant fame as an astrologer, making successful, if sometimes a bit vague, predictions about severe weather and geopolitical events, like a Turkish invasion.
So why the harsh dismissal? Why call it a stupid daughter?
Well, he had to survive. He lamented that the highly wise astronomy, which he called the mother, would simply starve if not for the daughter's earnings. He was frustrated by the sheer absurdity and superstition often demanded by his clients.
But he didn't reject the core idea outright.
No, and that's the key distinction, isn't it? He sought to reform astrology. He tried to separate the prejudices and superstitions, like reading bumps on the head or predicting specific lottery numbers, from what he believed was a genuine, measurable causal link.
He was looking for a rational, physical basis for it.
Precisamente. He hypothesized that the configuration of the planets at birth might genuinely influence the inclination or the temperament of an individual, similar to how the moon influences the tides. He wanted to strip away the magic and find the physics.
And that ambition just highlights the constant financial desperation that defined his life.
It's tragic. He was constantly battling poverty. By the time of his death, He was owed the colossal sum of 29,000 florins by his patrons, a fortune he desperately needed but never received. A man of his intellectual caliber forced to calculate horoscopes just to pay the rent. It's just, it underscores the chaotic reality he navigated every single day.
So, if that chaos defined his external life, geometry really defined his internal life. We need to shift now to the philosophical engine that drove his greatest discoveries. His absolute conviction that the universe was designed by a perfect geometric God.
For Kepler, geometry was literally the language of the creator. He wasn't just using math as a tool. He was pursuing theology through numbers. That famous quote, "Geometry was before the world and was divine." That tells you everything you need to know.
He saw studying geometry not as a mere scientific pursuit, but as a way to grasp the mind of God.
And to participate in the beauty of the original design.
Yeah. This quest for the divine blueprint led to his first major work, the Mysterium Cosmographicum, or the Cosmographic Mystery. He published it when he was only 26.
And the goal was astounding. He wanted to explain the precise number and spacing of the planetary orbits using the classical Platonic solids.
This is such a beautiful, perfectly medieval idea applied to the new modern Copernican structure.
It really is. So the ancient Greeks had proved that there are only 5 of these regular polyhedra shapes where all the faces are identical regular polygons. You've got the cube, the tetrahedron, the octahedron, the icosahedron, and the dodecahedron.
And Kepler asks, why are there exactly 6 known planets?
Because there are exactly 5 perfect shapes, it had to be. He believed God must have used these 5 solids as the spacers, or the glue, between the 6 planetary spheres. He devised this incredible nested model.
Okay, walk us through it. It's like a geometric Russian doll.
That's the perfect analogy.
Yeah.
So you start with the innermost planet, Mercury. Its orbit is contained within a sphere. Around that sphere, he nested the first solid, the octahedron. Then the next sphere, for Venus, circumscribed that octahedron.
Okay, so Mercury, octahedron, Venus.
Right. Then around the sphere of Venus, he nested the icosahedron. And that was encased by the sphere of Earth.
And this just keeps going outwards.
Precisely. Earth's sphere was surrounded by the dodecahedron, which was then enclosed by Mars's sphere. Then the tetrahedron went around Mars, followed by Jupiter's sphere. And finally, the cube was placed around Jupiter, with Saturn's orbit circumscribing the entire arrangement.
That is an astonishing feat of imagination. I mean, it must have felt like he had found the ultimate truth of the universe.
He was ecstatic. He was sure this geometric arrangement proved the perfect wisdom and order of God's design. This wasn't just astronomy for him. It was the fusion of Plato, Pythagoras, Copernicus, and Christian theology into one coherent vision. It gave the cosmos a theological necessity.
And this deep spiritual commitment even extended to his concept of the cosmos mirroring the Holy Trinity.
Yes. In his mind, the Trinity was perfectly reflected in the solar system. The sun was the Father, the source of all light and power standing at the center. The planets were the sun, circulating around the Father.
And the force moving them.
That was the Holy Spirit, the anima motrix, the soul or power radiating from the sun that drove all the celestial motion.
But here's the tension. When he actually compared the known planetary distances from Copernicus with the geometric spacing from his Platonic solids model, the numbers didn't quite line up.
No, they were close, but not exact. And this is where his stubborn faith in the design really shines through. He acknowledged the discrepancies, but rather than discarding the whole theory, he concluded that the polyhedral structure was fundamentally correct. It was the intended blueprint of the God geometer.
So the data was just a little off.
In his view, yeah. The small deviations or gaps just meant that the observational data was slightly inaccurate, or that the design included minor refinements he hadn't uncovered yet. He was so certain of the geometric perfection that he believed the data had to eventually yield to the math.
This philosophical drive then resurfaces years later in his masterpiece, Harmonices Mundi, The Harmony of the World, where he connects geometry not just to solids, but to music.
He believed that musical harmony was also divine. It's based on these simple, elegant ratios, like 1 to 2 for the octave, or 2 to 3 for the fifth. So, since God used geometry, and music was based on geometry, music must also be encoded in the cosmos.
How did he translate celestial motion into audible harmony? I mean, he didn't think the planets were actually making noise, did he?
No, not literal noise. He thought the harmony was perceivable by the intellect. He meticulously linked the ratio of the numbers underlying those perfect musical intervals to the ratio between the maximum and minimum angular speeds of the planets as they moved through their orbits.
So when a planet is moving fastest, closest to the sun, and slowest, farthest from the sun, The ratio between those two speeds could be expressed as a musical interval.
Exactly. If that ratio approximated, say, a perfect fifth, then that part of the planet's orbit contributed to a perfect harmony. He conceived of this as the music of the spheres, perceivable only by pure souls or the intellect, a divine melody confirming the purposeful design of creation.
And it's important to remember this wasn't happening in a vacuum. His thoughts were informed by others who had dared to break the boundaries of the finite cosmos.
Yes, figures like Nicholas of Cusa, who had centuries earlier suggested the world was infinite and therefore lacked a center.
And then there's the much more contemporary and much more dangerous example of Giordano Bruno.
Bruno took it much further, advocating that the stars were other suns with their own planets, a truly modern vision. But the danger of these ideas was made horribly clear in 1600 when Bruno was burned at the stake for heresy.
So Kepler is advocating for a radical, sun-centered universe at great personal risk. He's constantly aware of the lines he couldn't cross, even as he was trying to prove divine order.
And that's the paradox, isn't it? He needed to find the perfection of the sphere, but he was about to discover that he needed the hard numbers of an elliptical universe to do it.
So Kepler had the theory, the religious motivation, and the geometric conviction. But, as we talked about, his eyesight was terrible. He desperately needed accurate data to test his elegant hypotheses against reality, and that necessity led him straight to Tycho Brahe.
This partnership, which began in 1599 in Prague, was scientifically essential, but personally explosive. You had the greatest observational astronomer who ever lived meeting the greatest theoretical mathematician.
And they couldn't stand each other, but they absolutely needed one another.
The character contrast is staggering. Tycho was this aristocratic figure of immense wealth and ego. He had his own island observatory, Uraniborg, which was basically a science fortress. He was famous for his eccentricity.
The golden nose.
The golden nose, right, which he lost in a duel. He kept a court jester. He owned a pet moose that allegedly died after drinking too much beer.
You can't make this stuff up.
He was extravagant and demanded total control. And he treated Kepler, who was perpetually poor and often ill, not as an equal collaborator, but as a subordinate assistant. He would mock him, and he certainly refused to give him full access to the most sensitive data. He was a data hoarder.
And Kepler, meanwhile, was impatient, convinced of his own geometric correctness, and, easily offended by the condescension.
The initial collaboration lasted just a few weeks before Kepler, fed up, fled Prague and sent this scathing letter to Tycho. He later apologized and came back because he recognized the simple truth. Tycho's data was the most accurate treasure trove in the world. It was accurate to less than 2 minutes of arc, an accuracy far exceeding anything in history, and an accuracy Kepler could never ever achieve himself with his poor vision.
The truce was pragmatic, but it was short-lived. Tycho died suddenly in 1601.
And in a twist of fate, Tycho entrusted Kepler with his entire legacy, the meticulously compiled observational record. Tycho's last words, according to some accounts, were a plea to Kepler.
Let me not seem to have lived in vain. And Kepler was appointed imperial mathematician in his place. He was finally the sole custodian of the raw numbers.
And Tycho had given him his supreme test, calculating the orbit of Mars.
Why Mars? Why was that the target?
This was a stroke of genius, whether it was intentional or not. Of all the known planets, Mars has the most eccentric orbit. It deviates the farthest from a perfect circle. It was the hardest planet to model using the old system of circles and epicycles.
So if there was a hidden flaw in the old theories, Mars was the planet that would expose it.
Precisely. And Kepler spent years laboring over this data, trying to force Tycho's perfect numbers into a perfect circular model. He was using all the complicated techniques, like shifted centers and imaginary points called equants.
And this is the hinge moment in astronomical history.
It really is.
Yeah.
He found that even his best circular model, after endless calculation, resulted in an error of approximately 8 minutes of arc when compared to Tycho's observations.
8 minutes of arc. That is tiny. It's about a quarter of the width of the moon as seen from Earth. I mean, most scientists of the era would have just dismissed that as instrument error.
But Kepler couldn't, because he knew how good the data was. He knew Tycho's observations were accurate to 2 minutes of arc. So if his model disagreed by 8, the model was wrong, not the data.
It was this absolute commitment to empirical truth over philosophical beauty.
He famously declared, "These 8 minutes, which cannot be ignored, will give us the means to transform all of astronomy."
And that slight deviation forced him to abandon the most sacred philosophical concept of 2 millennia, the belief in perfectly circular orbits.
An idea established by Plato and Aristotle, It was a monumental, probably heartbreaking intellectual leap for a man who worshipped geometric perfection. But reality, backed by Tycho's iron data, overruled his spiritual preconceptions. The result was Astronomy Nova, published in 1609, containing his first two laws.
So the first law defined the new shape.
The ellipse. It was a mathematical curve, not a philosophical ideal. The orbit of every planet is an ellipse, with the sun at one of the two foci. This meant the sun wasn't just the geometric center, it was a physical anchor at a critical point in the orbit.
You can picture that so easily with the gardener's method of drawing an ellipse, with the two pins and the string.
Right. And the second law simultaneously addressed the variable speed of the planets, which had previously required these cumbersome, confusing additions like equants to explain.
The second law, the law of equal areas, the line connecting the sun and the planet, sweeps out equal areas in equal intervals of time.
Which is just an elegant way of saying that planets move faster when they're at perihelion, closest to the sun, and slower when at aphelion, farthest from the sun. But what's fascinating here is the mathematical technique he used to get there.
The sources mention its similarity to early calculus.
It's very similar. Instead of calculating the movement step by step, Kepler divided the elliptical area into an infinite number of tiny triangles, much like Archimedes had done centuries before. He then summed up the area of these infinitesimal triangles. This method of dividing a continuously changing curve into infinite parts is exactly what integral calculus would formalize decades later.
So he didn't just find what the planets did, he found a revolutionary new way to calculate it, tying geometry and time together in a completely novel way.
He moved astronomy from descriptive geometry to analytical physics. And yet, even after these two monumental, physically rigorous laws, he still hadn't answered his initial mystical question. What was the grand, unifying geometric rule for the entire solar system?
The first two laws addressed the motion of an individual planet, but Kepler was still consumed by this quest to find the simple, perfect ratio that tied all the planets together, the secret key to the Harmonices Mundi.
He returned to this question for another decade. The third law, finally published in 1619 in that very mystical book, Harmonices Mundi, was the answer. After searching through every possible numerical ratio, he found it.
The third law of planetary motion. The square of the period of a planet's orbit, which we call 232, is proportional to the cube of the semi-major axis of its orbit, or 353 times.
It's a mathematical statement of cosmic harmony. It's simple, it's elegant, and it's universally applicable to every single body orbiting the sun. It was the beautiful geometric relationship he'd been seeking since he first thought of the Platonic solids model, only this one was empirically verifiable.
Let's just illustrate the immense power of this, especially using astronomical units, where Earth's distance is 1 AU and its period is 1 year.
Okay, so if you look at Mars, which orbits at about 1.52 AU, cube that distance, you get approximately 3.53. Take the square root of that, and you get 1.88. A Mars year is 1.88 Earth years.
And it works for everything.
Everything. Saturn is about 9.5 AU from the sun. 9.5 cubed is about 857. The square root of 857 is about 29.3. And Saturn orbits the sun in 29.3 years. It just works perfectly.
So that simple function, 2 tau 2, is proportional to A3 Anthrax. It unified the entire celestial system under one single rule.
And this is the moment Kepler transitions from a brilliant observational theorist to the first true astrophysicist. He rejected the ancient idea that astronomy was just about describing movement. He insisted that astronomy is inseparable from physics. He demanded to know not just how the planets move, but why they obey these rules.
Which led him to hypothesize this sophisticated proto-gravitation theory that is, frankly, remarkably modern.
He argued that the sun must be the engine, emitting a force. He likened it to a magnetic force that drives the planets. And crucially, he deduced that this force must weaken with distance. This explained both his third law and his second law.
And he even anticipated the critical mechanism of how forces attenuate in space.
Yes. Kepler observed how light intensity decreases as the inverse square of the distance from the source. He surmised that the sun's moving force must follow the same principle. He lacked the tools to prove it, but the intuition was spot on. It would form the mathematical backbone of Newton's later gravitational law.
It's often said that Newton's greatest discovery was Kepler's notes, but the similarities go way beyond the inverse square relationship. Our sources highlight his profound insight into mutual attraction.
This is the truly stunning piece of foresight. In 1605, Kepler was already thinking about attraction not as a one-way street, but as a universal mutual force. He wrote that if you place a stone outside Earth, the stone accelerates toward the Earth. But he continued. The Earth would accelerate toward the stone.
He anticipated the law of equal and opposite reaction, Newton's third law, decades before Newton was even born. That just shatters the ancient philosophical hierarchy of perfect celestial bodies.
Absolutely. The dominant view since Aristotle was that the Earth was gross and heavy, but heavenly bodies operated on different principles. Kepler saw attraction as a mutual relationship. He even concluded that they divide the space between them inversely proportional to their weights.
That is a clear, if rudimentary, definition of universal attraction based on mass.
It is.
So, given this incredible intuition, what was the physical error that prevented him from becoming the full discoverer of universal gravitation?
His critical error was in the source of the force. He believed the moving force came from the sun's rotation, acting like a rotating magnetic field that dragged the planets along. Newton later realized the force came from an object's mass, regardless of rotation, acting in 3 dimensions.
So Kepler correctly identified the geometry of the force, but incorrectly identified the motor.
Precisely. Although in his search for evidence of the sun's rotation, he correctly identified sunspots, even though he first misinterpreted them in 1607 as a transit of Mercury. So even his errors led to new discoveries.
What's so fascinating is how these foundational laws are still used today. They are not just historical footnotes. We use them to detect things we literally cannot see, like dark matter.
It just demonstrates the ultimate durability of his mathematics. If we observe a spiral galaxy, the stars orbiting near the center should follow Keplerian dynamics. But the stars on the extreme outskirts, far from the visible mass, should move much slower.
But observations show they don't slow down as expected.
Exactly. The orbital speeds in the galaxy's outskirts remain unexpectedly high. This non-Keplerian rotation tells us that the visible mass, the stars and gas we can see, is not enough to generate the gravity needed to hold the galaxy together.
So there must be something else there.
A massive, unseen halo of non-luminous material dark matter. Kepler's laws act as the baseline against which we measure the strange dynamics of the universe.
And we also use his laws, specifically the ellipse, to weigh the supermassive black hole at the center of our own galaxy.
Yes. Scientists observe the star S2, which orbits the galactic center in this tight, highly elliptical path. By observing that precise elliptical orbit, Kepler's first law, and using the third law relationship, they can calculate the immense central mass required to keep S2 in that orbit. And that confirms the black hole's mass at about 4.3 million times that of our sun. Kepler's rules remain the core tool for calculating cosmic masses.
We've focused so heavily on the 3 laws, but Kepler's genius was multidisciplinary. He didn't just transform astronomy, he transformed how we see, literally. His work in optics was revolutionary.
His contributions here were immense and often driven by necessity. His initial optical studies, detailed in Astronomy Pars Optica, were motivated by the practical need to correct astronomical measurements, especially those taken near the horizon.
He had to account for atmospheric refraction, the bending of light by air.
Exactly. He developed the geometric theory of optics we still use today, with ray tracing diagrams. But his most significant contribution was solving the puzzle of human vision. He provided the first correct explanation. The image is formed, inverted, on the retina, and it's the brain, not the eye itself, that perceives it as upright.
And he didn't stop there. He used this knowledge to address his own lifelong visual defects, explaining the mechanisms behind myopia and hyperopia.
This anatomical understanding then allowed him to radically improve the tools of the trade. Shortly after Galileo demonstrated his telescope, Kepler published Dioptris, where he proposed a vastly superior design, combining 2 convex lenses instead of Galileo's convex and concave combination.
Why was the 2 convex lens model better for astronomy?
Well, while it produced an inverted image, which doesn't really matter for observing stars, it offered a much wider field of view and higher magnification. This design became the foundation for the modern astronomical telescope. He was both the theoretical giant and the practical inventor.
If his laws were his divine inspiration and his optics his anatomical genius, then the Rudolphine tables must have represented his professional martyrdom.
It was an immense undertaking, spanning 20 years of his life. Tycho had observed. Kepler was tasked with compiling that massive data set and critically reconciling it with his own new elliptical Copernican model.
The goal was to create the most accurate tables ever produced for calculating planetary positions, essential for navigation, map-making, all sorts of things.
But the struggle to produce these tables was defined by hardship. He had to perform all the incredibly tedious, multi-digit arithmetic calculations himself. This is before mechanical calculators. He faced constant interference from Tycho's highly litigious heirs who were always demanding credit and profits.
And of course, the debt. He was constantly begging for money to pay the printers. Emperors Rudolf II and Matthias owed him that staggering 29,000 florins.
The irony is so powerful. Kepler knew 3 laws would last forever, but the Rudolphine tables, the project that consumed his professional life, would eventually become obsolete. It was the price of empirical science versus eternal law.
Now let's talk about his work that transcended science, Somnium, or The Dream. This is widely considered the first true work of science fiction.
Somnium is a masterpiece of intellectual subterfuge. It frames a fictional trip to the moon, which he calls Lavania. By using this fantastical device, he created a safe, detached space to argue for the heliocentric model.
Because if the reader sees Earth revolving around the sun from the perspective of the moon, the absurdity of geocentrism just disappears. It was a gentle argument, avoiding the fiery debates that silenced Galileo.
And within this framework, he embedded serious physics. The sources note he used the lunar setting to discuss gravity and tides. He wrote that the sun and the Earth exert gravitational influence on the waters of Lavania. This concept of differential gravity causing tides was a significant precursor to Newton's work. He was using fiction to prove physics. He also tackled one of the grandest cosmological problems, one that still bears a different name today: Olber's paradox.
Right, the darkness of the night sky. When Galileo's telescope revealed the universe was filled with vastly more stars, it reignited the debate. Was the cosmos finite, as Kepler believed, or infinite, as Bruno had suggested?
And Kepler realized that if the universe were infinite and static, the entire night sky should be blindingly bright. Every line of sight should eventually end on a star. But it wasn't. It was dark.
His immediate resolution was that the universe must be finite. While we now know the darkness is resolved by the finite age of the universe, the fact that Kepler even articulated this profound contradiction shows his incredible cosmological foresight.
And to wrap up his complex intuition about order, there's that perfect final anecdote about his wife, Barbara, which touches on thermodynamics and entropy long before those concepts existed.
It's a beautiful philosophical reflection. He asked his wife, Barbara, if all the separated ingredients of a dinner salad, the oil, vinegar, salt, lettuce, could fly into the air and after an eternity of random motion, spontaneously reassemble themselves into the perfect dish they were about to eat.
The idea being that random chance could eventually create order.
But her response was immediate and intuitive. She said, but they would never be arranged with such elegance and in such perfect order as now. Kepler used this to argue for a deliberate creator, but it reflects this deep, intuitive understanding of irreversibility, that natural systems tend towards chaos, not perfect, spontaneous order. It's a grasp of entropy found in a simple dinner conversation.
That story just captures the heart of Kepler. His need for perfection, his ability to draw profound principles from the most mundane circumstances, and his conviction that underlying everything was a beautiful, discernible design.
Synthesizing Kepler's life, you really see him as the single most vital transitional figure in the history of science. He was the last great thinker to treat astronomy as part of this theological and philosophical quest for divine harmony.
Yet he was simultaneously the first to subject that divine vision to rigorous, unforgiving physical law and meticulous empirical observation. He took Tycho Brahe's raw, hard-won numbers, the empirical facts, and transformed them into cosmic universal rules that govern every orbiting body, then and now.
His life ended tragically in 1630. He was driven from yet another home, still chasing payment for that massive salary debt, a casualty of the religious wars. The sources mention that on the day of his funeral, an unusually bright meteor shower was observed, followed by a lunar eclipse, a fitting celestial salute.
His intellectual path leads us right back to our initial paradox. He was driven by this intense, mystical, Pythagorean belief in the perfect beauty of divine geometry. He was looking for God's perfect circular design in the universe.
And his monumental discoveries, the elliptical orbits, the variable speeds, and that perfect relationship of T-dual Russian prop A303 were achieved precisely while trying to prove that mystical harmony. He used the perfection of the geometric mind to find the imperfection of the physical universe.
So we'll leave you with this provocative thought to consider. Kepler faced constant persecution and poverty because he refused to discard his theology. He sought unity and beauty first, and the mathematical laws followed. Could he have actually succeeded in his discoveries if he had chosen a purer, more mechanical approach?
Was the very thing that made him seem archaic to his peers the geometry, the theology, and the relentless search for cosmic poetry, was that actually the necessary engine that allowed him to make the most revolutionary scientific discoveries of his age. We'll leave that beautiful, chaotic tension for you to ponder.
Join us and keep your curiosity well fed. Who knows? The next video might be exactly what you didn't know you needed.